Hi everyone and welcome back to the official STEMfairies YouTube channel. My name is Sameeksha and in this short video we will cover the IGCSE topic of graphs of motion. Now I'm sure we are all familiar with the basic concepts of speed, time and distance and how these three units help us understand the physics of moving objects and basic concepts of motion. We also know of the concept of SI units and how they help physicists and students around the world to make calculations easier. We are also aware of the general formulae for finding speed, distance and time when two other units or values are given. We know that speed is equals to distance over time, and to find any of the other two values, you rearrange the equations. We also know that average speed is equal to the total distance traveled by an object over the total time taken. Now that we have gone over and summarized what we already know, let's move on to graphs and representing speed, distance and time in a standard XY axis. Let's begin with the easiest one, the distance time graph. Now as you can see in the graph, time is represented in seconds on the x-axis and distance in meters on the y-axis. We have taken SI units so as to keep it simple for all of us. Now let us consider a car moving between 2 points A and D with stops in between at B and C. If you look at the standard formula for speed, it is distance over time. And as we've all learned in math, the gradient is the y-axis value over the x-axis value. Now since the y-axis value is distance and the x-axis is represented by time, the y over x-axis would equal distance over time, which is speed. So that would tell us that speed is the gradient of the graph at a certain point. Now speed is not necessarily constant between a certain distance and time graph, because as you can see, the line continuously changes. The car does not necessarily cover the exact same amount of distance in equal intervals of time. Now let's look at points A and B first. As you can see, there is a difference in the y-axis values, that is the distance axis, as the car moves between points A and B. This indicates that the car has moved a certain distance, and obviously for that it would need certain time. Now, although we don't have exact values depicted in this graph, we can easily see that there is a certain amount of distance covered in a certain amount of time. This proves that the car does have speed in this current part of the graph between points A and B. So we can conclude that between points A and B, the car is moving with a certain speed, covering a certain amount of distance in a specific time interval. Now let's move to points B and C. The line between B and C is considerably steeper, and as we've all learned in math, when the line of a graph is steeper, that means the gradient is higher. And since in this case speed is our gradient, it would indicate that speed is higher than it was between A and B. Now what does this mean? More speed means more distance covered in a shorter time or in the same amount of time. Now ideally, in a practical situation, the graph would also show us an increase in speed, which would mean that around the point where B is placed, the graph would actually curve upwards towards C and until it became a straight line. But let's not look at that now. That would indicate that the car is accelerating, which we will cover in a few more minutes. All we need to look at now is that between points B and C, the speed is considerably higher than it was between points A and B. Now let's move to the points C and D. We have a flat horizontal line. Now although between points C and D you can see that the x value, that is the time increases, there is no increase in y value, which means the car is not covering any distance over a period of time, which indicates that speed equals 0. The car is stationary, the car has come to a stop. This last section of the graph is quite easy to understand. Distance is 0, and since 0 divided by anything, any amount of time is 0, speed is 0. In a distance time graph, the gradient of the line represents speed, and in the graph that we can currently see, all these lines are straight, which indicates that speed is a constant value. We have not taken acceleration or changing speeds into account, which obviously is not practical because any moving object, when it changes speed, it accelerates or decelerates, which is a decreasing acceleration. But just for the sake of an introductory graph, we can assume that speed changes immediately. Now that we are done with the basic concept of a distance-time graph, let's move on to the next part, acceleration. Now, the basic definition of acceleration is the rate of change of speed. When we talk about rate, we refer to time. So when you say rate of change of any value, you are determining that certain value divided by time. So in simpler words, acceleration is simply speed over time. But keep in mind too that value of acceleration itself can change. So the formula that we just deducted, speed over time, refers mainly to constant acceleration. That is when there is no change in the value. Now, what about when an object is slowing down? That is known as deceleration, which is basically negative acceleration. So if you were to look at it as a value, let's say if the acceleration of a car was 5 meters per second square, the deceleration, if it was decelerating at the same rate, it would have been minus 5 meters per second square. Now, meters per second square. Where did I get this from? Now, we know that the SI unit of speed is the SI unit of distance divided by time, which is meters over second, which you could also call meters per second. And now, since acceleration is speed divided by time, we would count it as meters per second divided by second. So the seconds turns to second square. Now that we've gone over the basic concept of acceleration, let's move to a speed time graph. As we saw in the distance time graph, since speed is the value of distance over time, we deduced that speed was also the gradient of a distance time graph. Now the same thing applies to acceleration in a speed time graph. Since acceleration is a value of speed over time, we can infer that the gradient of a speed time graph would equal the acceleration of whatever moving object it is we're taking. One more thing that we could add in a speed time graph is the distance in a speed time graph. Now, if you look at the graph in front of us, we have shaded it in 3 different colors, yellow, blue, and green. Now, to calculate distance from a speed time graph, although we don't have the values here, distance is the area under a speed time graph, which is the shaded area that we have in front of us. I have divided it into 3 different sections just to make it easier for all of us. Now, let's say we wanted to find the distance between points A and B, which would be the yellow region of the graph. We would simply take the area under that part of the graph, which is the yellow triangle, which is nothing more than the area of a triangle, which is half times base times height. And the same applies to the area between B and C and D and D and E. Now, under a curved graph, it becomes a little more complicated, but the concept is the same. The area under the graph, one could even count the blocks under the graph to get an estimate of the distance covered. Now, moving back to acceleration, the line between points A and B in the graph. It is a straight positive gradient. Positive indicating that car is accelerating, that is speeding up. And since it's a straight line, we can say that acceleration is constant. Now, do not confuse this with speed being constant. Speed is increasing at a constant rate. Acceleration is constant, but speed is not. It's a little difficult to wrap your head around this concept at first, but you will understand over time. Now, that part of the graph was pretty straightforward. Now, let's move to B and C. This gets a little more complicated. So, if you look at somewhat first half of the part between B and C, it's almost a straight line, which means that the car is going at somewhat a constant speed. That is, acceleration, the gradient of the graph is 0. But if you look at the second half, it's a curve. The graph is curving upwards, which means that the gradient of the graph, if you were to take a scale and point it as a tangent at different parts of the graph, you will notice that the scale is getting steeper, which means the gradient is increasing, therefore acceleration is increasing, which means the car is not only speeding up, it is speeding up with increasing acceleration. Now again, back to points C and D, it's the same concept that we we just took in the first half between B and C. It's a horizontal straight line, and if you look at the speed, the y-axis, there is no change in speed, which means acceleration is 0. Now on to the last part, the graph between D and E. Now the gradient is not moving upwards, the gradient is downwards, which would indicate that it is negative. And as we spoke about a few minutes ago, negative gradient is negative acceleration, which means the car is decelerating. That is, it is slowing down. But again, the graph is not a straight line downwards, it is curving, which indicates that the value of the deceleration of the car is not constant. Now, if we again were to take the scale method and started from point T, the scale actually gets less steep as we go towards E, indicating that the value of the deceleration is decreasing, which means that the car is not only slowing down, it is slowing down with decreasing deceleration until it comes to an absolute stop at E. Now, one common mistake that people make with speed time graphs is assuming that when the graph is flat, as in horizontal, at any certain point of the graph, the car is stationary or the object is not moving. But this is mainly because we confuse it with the distance time graph, wherein when the graph is flat at a certain distance, the car is not moving. But keep in mind that over here, the y-axis is speed, which means even though the graph is flat at a certain point, the car or object still has speed, is still moving, it's just the acceleration that is 0, which means the car is neither speeding up nor slowing down. Now, that about covers the difference between the general concepts of speed time and distance time graphs and the difference between them. Let's wrap it up with comparing scalar versus vector quantities. This is more of a reinforcement since we all know what they are. Scalar quantities are something that have magnitude but no direction. Magnitude is basically the value. Now, if you look at speed, you can say that a certain object is moving at, let's say, 4 meters per second or 50 kilometers per hour. This 4 and this 50 is what is known as magnitude, which means that the value that we have, it can be quantized. You can give it a number, but it does not have direction. If I was to say that a car is moving at a speed of 50 kilometers per hour, it does not signify in which direction it's moving. But at the same time, if you look at velocity, a vector quantity, it is something that has both magnitude and direction. If I had 2 points A and B, and let's say that the direction from A to B is positive, and if I were to say that a car is moving at plus 40 kilometers per hour, you could tell that it is moving from A to B, which means that velocity is determined by its direction. It is a vector quantity. A few more examples of scalar quantities are distance, mass, work, volume, and vector quantities, displacement, weight, gravity, and so on. Now, as we get older, the difference between scalar and vector quantities becomes more stark, and now that we've looked at speed time graphs, you would start looking at velocity time graphs, which means that you could also tell when a car or a certain object is moving in the opposite direction, that is, when the velocity is negative. Now, this about concludes our chapter for the day. Remember, the difference between a distance time graph and a speed time graph is not great, but very important. I would like to thank you all for watching this video today, and I do hope that my explanation of this topic proves to be a good introduction to what you have to study in the future. Thank you very much again for watching, and don't forget to subscribe to the STEMfairies YouTube channel for more videos like this in the future.